Okay, can you see my screen? Can you see my screen now?
Yes. Yes.
Okay. Okay, I'll begin. Well, I'd like to actually thank the organizers for inviting me to this event. I wanted to be there, but it turned out that I have other events, and the journey is actually quite long. So I decided to do this online. The topic of my talk today is multimodal foundation and large language models. As you know, this is probably one of the most hot and popular topic. One of the most hot and popular topics in recent years. And in this talk, I'd like to actually go through a little bit about multimodal foundation models. So I'll give you some introduction and some challenges and applications that we are doing currently. And then I'll have some concluding remarks. Now, many of you may know what a language model is. A language model is basically a machine learning model that aims to predict and generate a plausible language, or in this case, possibly a next word. So given that you have input a lot of text, and then you could calculate the probability of a word that will occur following a word. And this probability will have certain kind of distribution of the word choice. So if I say I kick the, and I give you a blank, I kick the what? I kick the ball, or I kick the chair. But it's not very likely that you would say I kick the sun or the moon. It is possible, but not probable. Okay, and that's basically it's a language model. And the large language model is basically a modern version of the transformer-based language models with well over 100 million parameters. So these are, some of the things that like BERT, Lambda, GPT, and so on and so forth. Okay. So foundation model is basically an umbrella term that describe also a large language model. Or in fact, you could say that large language model is a form of foundation model. Foundation model is basically a model trained on a broad data. You can see that is on the left side. Maybe I could use this laser point. Yeah, you can see this on the left side. These are the data. Okay. The foundation model is basically have some kind of pre-training, okay, and then adaptation to the downstream task. So what you could do here is, focusing on the data, a very broad data, and then this could be a LLM, BERT, or whatever you have. And the downstream task could be sentiment analysis, question answering, and so on and so forth for text, or maybe for object recognition for visual data. Okay. However, what is being passed actually is being trained on single modality. Okay. But more and more recent years, multimodal data are available, and they are also being used to train these foundation models. And this is why we talk about multimodal foundation model. Let me just walk you, down the memory lane. Okay, so if you look at this chart, it actually has many interesting architectures, from BERT to GPTX to Stable Diffusion. And Sora is something that actually Nobody knows how it's being done. But it turned out that this is Sora right here. Somebody actually reverse engineered Sora, which is a generative video, model. Okay, so let's maybe just go through some of these things. So ChatGPT is basically a multimodal language generation. So you could actually generate images, text, and you could ask it to understand some of the images that you could input to. Stable diffusion, for example, this is the text to image generation. And you have Sora, which is a text to video generation that is being recently very popular. And then if you have not tried this, you could try Suno. Suno is a text to music generation. So you could say very easily, for example, generate a song that is in hip hop style that talks about this particular workshop that we have right now. Okay. And it will actually generate not only the lyrics, but the song. And then you will match it and it will sing it back to you. Okay. So you can see that these modalities are actually more and more available and being prevalent. Now, I want to distinguish the difference between multimodality versus multi-view. Multi-view here, it could be the same object, but you have multiple view, and that's different from multimodality. Okay, so you could have a text that describes a racing car. You could have an image that display that car. You have the audio sound that is done by the car, and these are what we call different modalities. But if you have this, you have the multiple images that has a multiple view of the same car. That's actually multi-view. That's not multi-modality per se. Okay. So models you learn from multi-view data, and what we want to achieve is basically a model, a foundation model or a large model that will be able to do multi-modality. Okay. So let's take a look at this. So earlier days, okay, so very, very early on, we talk about this probability, right? So on the left, you have paragraphs right here. And these paragraphs can be broken down into words. The words, you have bag of words. You have also term frequency, inverse document frequency, TF, IDF. And from here, you could probably predict if you do bigram, for example, you take two words together, then giving the first word, I, and the second word could be love. I love this movie. This is two words called bigram. This bigram could actually predict the probability of the next word occurrence. And this was useful, okay? And this was basis of also the language model that what we are doing currently, okay? In 2013, word2vec became very popular, and it was a breakthrough. Why? Because in addition to the word that we could predict the probability, we are now able to actually embed a word. And what that means is this: we could actually transform a word into a vector. And then to say that these words could, if they are similar words, their Euclidean distance could be very similar as well. For example, king and emperor, their embedding will be closer together than, for example, king and queen, or maybe king and house. Okay, so king and emperor will have a closer Euclidean distance. This facilitated the embedding of discrete data, such as word, into a vector. into a point in the high dimensional space. Go back a little more, 1982, this is where we had what we call the recurrent neural network, RNN. And the recurrent neural network right here, it was developed in 1982. And this was a network that is capable of processing temporal signals. But it was very rudimentary, very basic. It took another 15 years, right here, where Jürgen Schmidt-Huber developed this long short-term memory, LSTM, in 1997, 15 years. And then another 15 years later, about gated recurrent network was also introduced to simplify the LSTM. LSTM had one advantage over the RNN. RNN had no memory, but long short-term memory, as the word implied, it has memory. So it could store things and it could release things. By having this memory unit here, it allows sequential process or temporal process of, say, words, right? Like we need sequence, right? The probability of a word occurring, word embedding, for example, will require sequence. Our language is a sequence of words, okay? I say that I kick the ball, that makes sense. But ball, the I doesn't make any sense at all. So the sequence actually has meaning. And by having this long short-term memory, it actually is capable of understanding or predicting sequences and the next sequence. The gated recurrent network, GRU, make the LSTM more accessible, and by simplifying the circuitry, and it still will actually be doing more or less the same thing. In 1917, this is one of the things that actually transformed the industry. The transformer was introduced. So this was not that long ago, in fact, right? So 2024, so 7 years ago. And transformer has this value, key, and query. Okay, and the key and the query meaning that I have a key value, and this is what a query is, and then you can learn these three pairs, V, K, Q, together. Okay, and then he has this multi-head attention thing, and so on and so forth. But the transformer was able to actually learn a lot more than the previous architectures. BERT was the first one who was able to actually use this particular architecture and was able to do something with text. For example, okay, and in 2018, the first version of a GPT, okay, generative pre-trained transformer model, and was actually introduced. Okay, and here you can see on the left side, this is actually the transformer, the GPT style transformer that is slightly different from that in 2017. However, back in the 2018, it was not so popular. I mean, people look at this and go, oh, okay, that was great. You were able to generate certain things. Okay, you generate a sequence of valid sentences and so on and so forth. But it was not until 2020, I remember in November 2020, where ChatGPT 3.5 came out, where we finally realized the full capability of what these transformer could do. So this transformer is really be able to actually generate text based on the input, a very large database of input text, okay, to generate sequence of sentences. Okay, that is in fact a reflection of what he has learned. But what they're more than just these transformers. They are a lot more. For example, fine tuning. There's guardrailing. There are many engineering tasks that really made the ChatGPT 3.5 what it is today. Okay. So let's take a look at another type of network, which is called residual network, ResNet. This was actually developed in 2015. And what it was really nice, this residue network, is that it is able to, by having these skip connections right on top, right here, skip connections, okay, it is able to actually, quicken some of the processings and being able to actually bypass certain layers. Okay, by having these residue network, it actually facilitates the visual processing. So earlier, BERT and transformer are for text. ResNet is actually for vision, computer vision. So these are actually networks that will process it. So here, each one is a layer. These are 3x3 convolution, 64, 128, 256. So it's like in a pyramidal network. Okay, so ResNet was introduced in 2015. The UNet was also introduced so that you have the encoding here and then the decoding here. So the input image tile comes in from here, and then it's being compressed, and then it's being decoded. This is the encoding, and here it's being decoded. Okay. So when you have this encoding and decoding thing, you're able to actually generate images. And by combining text that is associated with these images, you also will be able to generate images based on text. So stable diffusion is where key, value, and query are being trained, are being associated, right? And the diffusion process is actually, again, this is the way that images are being generated these days in 2021. Okay. Sora is the latest. Now, this is a video. Now, you might say, well, Sora is just basically, if I could generate image, then I could generate a stack of images. I think the idea is very, very similar to that, okay? So it's based on the diffusion model, potentially. We don't know what it is. This is a hypothetical rendition of reverse engineered Sora, okay? That was presented earlier this year. Okay? So you have the video, pixel video space that could be encoded and decoded right here, okay? And then from that, you're able to use the diffusion transformer block, okay, to be able to actually generate the video. And now Sora has been shown that is able to generate, lengthy video in a realistic format, which is fairly impressive. So I just want to share with you, this could be the timeline of what we have. You can see that there are lots of transformers, GPT-3, GPT-4 right now. We're looking for GPT-5. I know that, recently Claude 3.0 has just come out, and many of these models are actually coming out more and more so, okay? But you can see that the last few years has been a very, very interesting and very fast pace. And these are some of the foundation model right here. Okay, so Falcon, GPT-4, Palm, E, and so on and so forth. So DALI. So these really, the things happen in 2021 and until now. So this should be updated, but there were more and more models coming up. Now, how do we actually do multimodality? Okay. One of the ways that we could consider multimodality is to use what we call a mixture of experts. Well, what is a mixture of experts? Okay, so if you look at this large M here, this actually uses what we call a mixture of expert model. So the mixture of expert is this: instead of training multimodality all at once, I might be able to use a group of experts in each of the modality, for example, in vision, in text, and in what other domains you have. Okay, and then I could use a gated network so that it could appear that it could have this characteristic of multimodality. And that could be one of the easiest things to be able to do at this time, right? Human doesn't do that. Human, we are one system that we actually handle multimodality of data quite well, okay? But nonetheless, all I want to show you is the power of mixture of expert in that it actually almost catched up with the GPT-4, which is basically trained as a multimodal GPT. Okay, so having just a mixture of expert, you could almost achieve the same state of a GPT that was trained specifically for multimodality. So that's actually impressive. How does it work? Well, it turned out that, as I shared with you before, you have experts here. Okay? And then you have a gated network. And this gating network, depending on what is the input right here, I could actually open or close these gates. And these gates will be sum up and then actually go out and give you the output. So this is a rough view. A more detailed view, you can see that the gating with the multiple feed-forward network right in here, okay? The router basically will route. These are the gating network, okay? And these will actually send the input tokens into these kind of network so that it could be added and then normalize it before it's go to the outside as the output. So these are the what we call the switch transformer gated network for mixture of expert. So that is one way of doing it. Okay, but what I want to say is that in fact the challenge for doing this is these for a few things. First is that we don't have so many high quality multimodal data. Right now, single data is clearly we have abundance of that. We have text, internet is full of text, right? Image and text, yes. Video and text, not so much. So we're missing a lot of these things. So training of multimodal data is difficult. More so, it is also very imbalanced. Right now, the text part is very, very capable, while the image part, the video part, and other modality are not very, very developed. Third one is that it is very ambiguous. Okay, how do you actually connect different modality? How do you associate them together? And then lastly, when you do the multimodality, not doing the mixture of expert, you would actually have a very heavy computational overhead. Okay, so these are some of the challenges that we face. So here we illustrate, one is we lack high quality benchmarks, repositories. And you can see that these are, some of the things, question and answer of a particular image, right? Yes, we can answer them, but, we just don't have enough of these data to train with that. And also, you can see that ChatGPT-4 is way ahead of many other, other image-based or video-based capabilities. Okay, and the third one is, how do you build connection? Is it 1 to 2, 1 to 3, 1 to n, m to n, and so on and so forth. And then lastly is the computational overhead. Okay, so this is a really a lot that we need, a lot more computational power we need. So here comes the second part of my talk. The second part of my talk, I'd like to actually go over some of the things that our group, are currently doing, okay? And maybe this will inspire you. And if you're interested in learning more, please feel free to contact me. So here are some of the things we are doing. The first thing is multimodal LLM for science, And this is really interesting, is that, as I say earlier, we know ChatGPT is for generating text. And text is basically just a sequence of symbols. If that's the case, my question then to you is, are we able to do the same thing with molecule, DNA, protein? Because each one of this, for example, DNA, is just ACGT. And there are many different strands and many sequences, okay? Molecule is the same thing. Protein is the same thing. Now, obviously, DNA is easier because it's a string that you could actually do. Molecule is a lot more complicated because it has a three-dimensional geometry. So this three-dimensional geometry may not map easily into a string, okay, into a string like a sentence, okay. So, but nonetheless, how can we build foundation models for different scientific data? Can we do this? What if we built the thing for DNA and protein? Okay, so it turned out that you could treat protein as a sequence of amino acid, so that protein sequences, it can become what we call a natural language sentence. Then what you could do possibly is to predict the next protein token. And this has potential applications in drug discovery, right? And in treating disease, for example, okay, and so on and so forth. So to understand this, we have done a little bit of work on trying to do protein, molecule, and DNA into good foundation model. And here, the DNA foundation models is also something that it is possibly done. Here are different, different characteristic, okay? And, you can see this is exon, intron, proton, promoter, enhancer, and so on and so forth. And you can see that this is basically a sequence, okay? All these sequences can be seen as a sequence of words. So if we can see many of these DNAs, are we able to actually build a foundation model to do this? In fact, yeah, we could, and we are doing exactly that. Molecule is the same thing, but as I shared with you, molecule, the difficulty with the molecule is that the molecule is a three-dimensional structure. It has a three-dimensional structure. So it is a little bit more difficult to map it. But nonetheless, you have a projection from 3D to 2D, or even to 1D, okay? Even with that, you lose some information, but you still are able to actually get the sequence out as from a molecule and use that for your foundation model building. So this is some of the work we actually do. Is pre-training molecule representation with 2D and 3D modality. So it's equivariant or SE3 invariant, and we base this on contrastive learning, and we're able to actually generate some interesting result. Okay, so so some of these are major questions for science. How do you relate the scientific text to geometric data? So how do you say that this DNA may actually have caused this type of disease, so that we know? Okay. So that next time, if we see these symptoms, we're able to verify whether this DNA, or we can actually find other DNAs with similar, context. Second is, how do we leverage different modality view of data? Molecule graph, 3D molecular conformer for better learning. And then how do we design novel self-supervised learning strategies for different scientific applications, such as drug discovery? And I like to actually share the second application here is multimodal for a foundation model for healthcare. One of the things that we want to do is to associate this doctor's report with images. So we get the doctor report, these are the report, and the diagnosis could be lymph nodes and so on and so forth at this segment. And what we want to be able to do is this, from these pathological images here and with the reports here, we want to be associated not only to diagnose, okay, to analyze where the tumor or the cancer is, but we want to be able to predict, and that's a much harder problem, is to predict where those cancer would be, okay? So these patches, okay, this whole slide images right here, and these patches are actually associated with this text right here, okay? The pathological report, unfortunately, is very unstructured, and it has a lot of redundant, again, unuseful information. And how do you actually associate these two for the prediction of cancer is a topic that we actually have done some work. And this is actually the foundation model for the WSI analysis. So this paper, okay, an LLM is used to extract the pathological description, and this is actually associated in a contrastive learning and to be learned for prediction of cancer and tumor. Okay. So yeah. So again, given the presence of mixture of this, what can be deduced from the single image regarding the possible diagnosis? So this can be generated, okay, when you actually have these this inside your foundation model, and the Quell Lava could actually generate this particular piece. Okay. So this is again image and text, but this specific modality right in here. Okay. So again, maybe I won't go into too much detail here for this particular one. The next one I want to share with you is the work that we have been doing is about the embodiment of AI. And this is a work that we want to associate vision, language, and action. Now, it is very easy to say, oh, image and text, right? Okay, good. But what about image, text, and the robot's action? Can we actually put these two together? Like, for example, put strawberry into the correct bowl. Okay? This is a word right here, and this is an image right here. But the action is to put the strawberry. You need to identify what are the strawberries. Not an apple, not something that is green, but this, the strawberry, put this into the correct bowl. You're not going to put the strawberry in along with the apple. You're not going to put it in this green bowl right here, but you want to put it in the correct bowl. Pick up the bag about to fall off the table, not this green bag, which is not going to fall off the table. You need to understand. So there is an understanding of this. There is a visual cue that you need to know which one is going to fall off the table. And then lastly is the action that you're going to train to actually pick up that bag that's about to fall off the table. And this involves multimodal data. It involves the language, pick up the bag. It involves the vision, looking at the bag. It involves the action, where is to go there and pick up the thing. So this is a very nice illustration of what we call a multimodal embodiment of AI. Okay, and this is really interesting and important. And this is basically, I just want to say this is a lot of high capacity model exists. Recently, we wrote a survey. So if you go on the internet right now, if you search for my name and VLA, Vision, Language, and Action, you will find a survey that we basically survey the foundation model that could actually combine these three modalities together. I really truly believe that this may be one of the last frontiers that we have, because the vision and language has been married for a long, long time. You know, ChatGPT could do these two very well, but it has not been embodied into robots. And this is really a recent seminal work that we have done in terms of having a survey on VLA, Vision, Language, and Action. And you can see that, you know, Dreamer 2020 all the way up to ChatGPT Robots 2023, the various development, their strength, and their advantage. So if you're interested in this, please take some time and then read our survey paper. So I just want to quickly illustrate the difficulty of doing something, putting all three things together for foundation model. You have a very high level command, say clean the room, right? So your high level planner might say, okay, you need to pick up the toy car, move the coffee table, put it near the camera, and so on and so forth. These are still very high level things. How does it actually go being embodied into these low level control policies? Like pick up the toy car. You know, these are the toy car, right? How do you pick them up? Where do you go? Are these actually, they should not belong to where they supposed to be? And where do they belong? Okay, all these things are good questions. Now, if you don't have a good knowledge in the worldview, then you will not be able to do this, okay? So the VLA basically takes the pre-training model, just like a foundation model. You know, if you learn so many tasks about picking up the cars, then you will be able to actually know how to pick up the car. And this is the exact same way that we want to be able to train. But one thing is we're lacking a lot of data to say picking up the car with a 3 or 6 degree of freedom of robot arms, how do you pick up the cars? You know, and what do you do? And how do you translate the high level command here into what we call a low level control policy? Okay, this high level planner into low level control policy. And these are really some of the issues that we are struggling with. One of the ways that, you know, there are two ways, basically two big ways to do this, is that you're able to actually use an LLM, okay, to be able to say, clean the room. This is a high level. Give me the breakdown of clean up the room. If I detect the object, toy car, or trash on the floor, then I'm going to just go ahead and pick up the toy car, pick up the trash. This is what we call a language base. But you know that LLM could also generate code. It could generate Python codes. It could generate programming codes. And here, what it will do, maybe the LLM will be able to generate the APIs, like a sequence of code to say, oh, detect the objects, and then do the pickup of the particular object, because here is the control policy. So this is will be language-based, and this will be code-based. And these are basically the two big ways to do this, okay? And here, some of the different architecture, cross-attention, FILM, concatenation. It turned out that I think this one is it this one. Yeah, the concatenation is the prevailing method of vision language fusion for transformer action decoders right now. Okay, so the challenges is that VLA, the data is so scarce. Okay, so we're trying to actually generate more data so that we could train on a large scale. And then real-time responsiveness is also very difficult to obtain. And obviously integration and also lots of safety considerations. We might be making robots too powerful. The next thing I want to share with you, oops, this thing is a little hard to read, is about hyperbolic embedding. And I want to go through this perhaps a little bit more quickly, is because I just want to share with you that we live in a kind of Euclidean geometry, but really, our Euclidean geometry is that parallel line stays in parallel. But there are also other type of geometry, for example, spherical geometry and hyperbolic geometry. Spherical geometry is what we live on Earth, in fact. Okay, so on a small scale, perhaps we live in a Euclidean geometry because the localized space is perhaps orthogonal. But you and I know that we live on the Earth, so it's really, we live on the spherical geometry. Why do I want to talk about the hyperbolic geometry? It is because hyperbolic geometry turns out that it has actually a good property. What is that good property? The good property is that it is actually good for what we call a hierarchical embedding. Okay, so if you have things that is hierarchical in nature, for example, a knowledge graph or a taxonomy of some sort, because most of our knowledge is actually organized in a taxonomy or in a hierarchy. If that's the case, it turns out that the hyperbolic geometry is the best that it could do. Okay, you can see here, hyperbolic geometry, eventually the multiple lines actually diverge. And this will actually give a good property. Why? I'll give you an example. If you're actually representing a tree, okay, when you put a tree inside a Euclidean space, such as like right here, the tree, these edges, nodes will become clumped together. Why? Because it's flat, okay? However, if you put this in a hyperbolic space like this tree, these nodes will be further apart, and they could be easily separated in the hyperbolic space, okay, because they are spaced when they are far away from the center. Okay, whereas this, okay, these will be close together, okay, when they are far away, right? But in the hyperbolic, they're actually further away. And with this property, it turned out that we have tested, it's actually good to be utilized to represent hierarchical information. Now, clip and Meru are the two ways to actually incorporate images and text. Clip is used in the Euclidean space, but Meru is actually embed images and text in a hyperbolic space for hierarchical information and hierarchical images processing. And we've been actually doing that, and there are several papers that we have done to do that. The challenge here is how do you effectively determine the suitable space? Is your data hierarchical enough that it requires hyperbolic space embedding? Second, how do you integrate different hierarchies from different source data? And then three, how to align multimodality of hierarchical embedding inside a hyperbolic space. So these are some of the challenges that we face. Now, some of you may be working on knowledge graph. And I'd like to just share very quickly with you about knowledge augmented methods for generative LLM. Now, you might know knowledge graph. Okay? Knowledge graph is actually very, strict. It's a very good structure. Large language, on the other hand, there is no explicit representation, whereas knowledge graph has explicit representation. So you have Obama right here, was born in Honolulu and is married to Michelle Obama. But in the large language model, all these things, when you say Obama, Barack Obama is married to, that is actually being predicted. Michelle Obama is not explicitly placed like knowledge graph, but it's actually, you could predict it from the probability from the input. So the pros about the knowledge graph is that it is very good structurally, it's very accurate, it's very decisive, and it's interpretable. So I know, Barack Obama is a politician, is a president of the United States, and so on and so forth. The cons is this: in order to build this kind of structure, it really takes so much effort. Lack of language understanding, it is also incomplete, because to build this, it takes lots and lots of effort. On the other hand, the large language model, what is nice is that it has a lot of general knowledge, because it seems so much input, it can actually predict what is the output without having a structure. However, these are implicit knowledge. He also hallucinates, and he's not totally decisive, because you ask this once, you ask the next time, it could be different. And it's very difficult to interpret what is saying, whether it is correct or not. Whereas knowledge graph, it is. The question then is, are you able to actually marry the two? Are you able to actually join these two, okay, together, taking the best part of the knowledge graph and the best part of the LLMs, and combine these two into something that is a lot more interesting? And the idea here is to unify on LLMs with knowledge graphs. And here is also a survey that people actually have beginning to do so. And this is actually quite exciting. It's almost like I don't know whether you remember, long time ago, there are two camps on how to do search engine. Yahoo actually was one camp, and they believe that there is a hierarchical approach. So they say, okay, you need to structure all your information, having news, local news, international news, sports news, financial news, So they come up with a taxonomy, a very structural approach to knowledge representation. Google say, heck with it. We don't have any representation. Everything is going to be just searchable. No, there's no representation. And you and I know who won at the end, right? Google eventually won because that fixed representation was very subjective. It was very rigid, and it takes lots of manpower to actually do that. Whereas Google's implicit type of search using PageRank won out. Same thing here. Can we actually combine these two for the betterment of LLM? And now I don't want to go through these examples, but these are some of the examples we have. And I think I want to perhaps just really want to say this. We're also doing some work with the watermarking. The reason why is we found out that there are a lot of fake stuff. It could be fake image. There could be text generated by ChatGPT and so on and so forth. So one of the things that we want to be able to do is to embed watermarking in the text, in the image of generated text and generated image, so that we can identify where they are from. Okay, so these are some of the work that we've also been doing, is to be able to put watermarks, okay, into generated ChatGPT generated text, or into the images that is being generated, so that we're able to actually detect where they are from and how it's being used. These are some of the work that's being accepted to some conference. You can take a look at it. I won't go through it here. This was actually a iClear 2024 paper right here. Okay, so again, we have our recent work being accepted. Okay, so I'll show you where it is. So I come to my conclusion, the future directions of multimodal foundation models. And one of the things is this, that we have to actually go beyond pairwise modality. So right now, a lot of multimodality is just text, image, text, video, and so on and so forth. And VLA, vision, language, action, is the first. It's one of the many, but one of the first few that actually integrate more than two modality. So what we need to do is obviously is go beyond the pairwise modality. But again, how do we get those triplet or even quadruplet data pair? And it's really, really tough. Okay. Exploring the connections among different modality is also it's also difficult. It's not that easy. Okay. How do you build repository? How do you build AGI systems? And so on and so forth. We need more benchmark. We need more data and more evaluation methods, and so on and so forth. And the last things I'd like to actually share with you is that as we build these things, I'm currently also working on trustworthy foundation models. And what we want to be able to do is that we want to be, when we build these systems, we want to be able to ensure privacy, accountability, safety, interpretability, and societal impact, and fairness, and so on and so forth into the system, so that we could build a foundation model that is trustworthy. So we don't want to just build a large foundation model, but we want to build trustworthy foundation model. So as we're building these foundation model, we need to be very mindful of all these aspects of things. So the conclusion of the talk today is that I hope you agree with me that multimodality foundation model and large language model is important. We need to actually incorporate image, audio, DNA sequence, action, and many other things into this multimodality foundation network. Okay, this really has the potential to revolutionize healthcare and science and many other things. Okay, however, I just want to say this: as we build this, we need to be very mindful about the privacy, about the fairness, and the ethical use, and so on and so forth. So when we build these systems, we need to have these things in mind. Okay, I would have to say that ever since 2 years ago, when I first saw the ChatGPT 3.5, I was amazed, and I'm continuing to be amazed at the pace of development of multimodal foundation models. I think the future is very promising. But please be responsible and be ethical in your development and deployment. And with that, these are some of the papers that we recently wrote in AAAI, HCI, KDD, NeuroIPS, Dept, and so on and so forth. So please go onto my DBLP page. There are lots of interesting things that have these papers on some of these topics that we have. And I just want to thank my students who are actually wonderful people who are actually helping me to further expand the research in multimodal foundation models. And with that, thank you very much.
Not coming. So actually, this is Dr. Sanjay. I'm from IIIT Bhubaneswar. So I'm working in the area of medical image analysis and healthcare engineering. So it will be great if you can suggest some area that we can implement LLM in the area of healthcare.
Yeah, so like a patient record understanding, and we already try to tie in the record, the healthcare record, or the pathologies record to the image. So I think a bigger project is to tie in the different modality. For example, you have the image, you have the sonar, you have the video, for example, of doing the endoscopic examination, for example. you could tie all this thing into actually a person's, to have a person's LLM, so that we could actually understand how those text records could be correlated or could be associated to, say, for example, the image and the video and the sound and genomic information and genetic information and other type of report. So I think more modality can be put in. That's all. Yeah.
Okay, great. Thanks a lot. I will connect with my team if possible, if you are available in near future. So I will
Sure.
definitely connect with you. Thanks
Sure.
a lot for your Thanks
Yeah.
a lot for your presentation and time. It was very nice presentation, and
Thank
it
you.
was very good for our participants of this workshop. Thanks a lot for your time.
Thank you. Thank you. Thank you.
Okay, see you. Bye.
Theo, bye-bye.